Huan, whenever you're ready.
Thank you, Liliana. So you can see my slides. Okay, cool. Yeah, hello everyone. I'm Huan. I'm a gravitational astrophysicist. So in the last talk of today, I'm gonna discuss some recent developments of astrophysics opportunities with Lisa. From the talk by Jess and John, we know that the astrophysical sources of LISA mainly are extreme mass ratio in spirals or these massive black hole binaries, or those galactic compact binaries. So in this talk, I'll be mainly focusing on the first two types of sources. So I will first discuss the signatures of the extreme mass ratio in spirals and talk about the formation and the rate estimate and why they're good probes for fundamental physics and astrophysics. And after that, I will discuss these massive black hole binaries. These are perfect sources of multi-messenger detections, and I'll discuss how to use gravitational waves to probe the delay time of the mergers of these binaries. Okay, so extreme mass ratio in spirals. So as John already mentioned, these are the system with one massive black hole, usually with mass 10 to the 5 to 10 to the 7 solar mass, and then a stellar mass object. This can either be a black hole or a neutron star or a white dwarf. So the separation between the smaller object to the massive black hole is usually, let's say, within 20 gravitational radii. Okay. So if we try to understand the dynamics of this system, we can use a perturbation point of view. So to the leading order, because of this very large mass ratio, the space-time is primarily the space-time of the large black hole. So the smaller object is just a perturbation to the background space-time. That means in the leading order, we can understand motion as a geodesic in a curved space-time. So we know that that motion is separable. So we can obtain the orbital frequencies in all these three directions in r, theta, phi. And then to the next leading order, we need to consider the gravitational wave effect by the smaller object. The gravitational wave will carry away energy and angular momentum. That means the orbit would shrink. And then to the next leading order, we have to consider the orbit goes from one geodesic to another geodesic with different energy and angular momentum. Okay, so typical this Emery orbit is in band for LISA for about 10 to the 4 to 10 to the 5 cycles. So this is actually very good, because if you convert this 10 to the 4, 10 to the 5 cycles to the magnitude of phase, total phase, that's about 10 to the 5 to 10 to the 6 radians in phase. Okay, so now if you imagine you observe this system for a long time, and somehow there is some additional small force acting on this Emery system, this additional force is only 10 to the minus 6 times smaller than the usual gravitational force. But then because you have 10 to the 6 radiant total phase, this fraction error of 10 to the minus 6 will contribute to 1 radiant phase change at the end. So we can measure 1 radiant phase change in the gravitational waveform. That means we can use this system to probe very small forces acting on the system. So that's why Emery is a very good probes for these fundamental physics or astrophysical environmental effects. Okay. Okay, so how do they form? So currently we understand that there are two main channels to form these Emerys. The first channel we call it the dry formation. So these are this channel is basically when you consider there is a star cluster around this supermassive black hole, and these stars scatter with each other, and sometimes it's scattered into a low angular momentum orbit and gets trapped by the supermassive black hole and form emery. So this is traditionally people understand how emery is formed historically, and people compute rate based on this channel. But in recent years, it is recognized that there's another channel which called VAT channel. So basically, if you have a supermassive black hole and there is a accretion disk, and these stellar stars in the stellar cluster would be trapped into this accretion disk and then migrate towards the supermassive black hole. And it turns out that this channel can also contribute to at least comparable rates compared to the dry channel. Okay, so let's look at this dry formation channel in a bit more detail. So basically, as I said, it's contributed by the scattering of the stellar mass object in the cluster. So it's scattered, the multi-body scattering scattered the one object to a low angular momentum orbit with small pericenter distance, and then it may lose a lot of energy angular momentum when cross the pericenter, and then it's gravitational bounded, and then it forms the emery. So this is the basic picture. So apparently, if you want to compute the rate, you have to understand the statistical evolution of the cluster with this massive black hole. This can be done with, let's say, the n-body simulation or this focal Planck calculation. This is what people did in the past. You can compute some intrinsic rate, which is dependent on the mass of the black hole, the primary black hole. But then depending on the different models of the cluster, you can estimate the LISA rate. So there is a huge uncertainty in this rate, right? So the most conservative rate and the most optimistic rate differs by a factor of 1,000, but the reasonable rate is roughly around 10 to hundreds per year. Okay, this is a dry channel. For this VAT channel with accretion disks, you can also compute the rate. You just have to model how this stellar mass object is interact with the disk. Basically, will generate density waves in the disk that carries away energy and angular momentum. And once it's trapped in the disk, it migrates towards the black hole also because of that. And you can do some calculation using this focal Planck formalism, and then you can compute the rate per black hole as a function of time for lifetime of this disk. It depends on time because the number of black holes available changes in time. So the rate is around 100 for if it's a dry channel formation, but then this rate, if there is a disk, the rate is much higher, as you can see. For massive black hole, for more massive black hole, the rate is even higher. But usually, the intrinsic rate between these two formations for given black hole is around, let's say, 100 to 1,000 for more massive ones, and 10 to 100 for less massive ones. But not all the black holes will have AGM disks, right? So roughly the fraction of black hole that has AGM disk is between 1 to 10%. So if you fold in this number, so it turns out that for LISA, this VAT channel will generate at least comparable number of emeries as these dry channels. So this is also a very important formation channel for emeries. Okay, So I mentioned previously about this MRIs being very good probes for fundamental physics. So how do we actually probe this fundamental physics? Okay, so there are two ways. So if the MRI system, let's say, carry some actual degrees freedom, maybe there is a scalar field in this stellar mass object. So the MRI motion will generate radiation with a scalar field, for example, or there is some accretion disk or dark matter cloud around the massive black hole, and the motion of the small object will generate this dynamic friction effect. So both cases, there are actual dissipation in the system, so we can measure the effect due to this actual dissipation. So this is one class of interactions. The other class of interactions is when you consider there are some conservative force acting on this MRI system. Usually these forces are not important in the long-term evolution, but except those so-called resonances, well, these three orbital frequencies are commensurate with each other. Well, one can show that the conservative forces will change, and for example, the angular momentum or Carter constant. So I'll come back to this. So let's see some examples for this first effect, this dissipative effect. So as I said, if you have this stellar mass object moving in some accretion disk, or there is some dark matter spike or axion cloud around the supermassive black hole, there is usually a friction force acting on this smaller object called dynamical friction, or there is some actual field radiation. The gravitational, the radiation back reaction is also dissipative. So if you, for example, take this axion cloud as an example, so this cloud can be generated while this so-called black hole superradiance process, and the smaller object moving in this cloud. So this friction force will take away energy and angular momentum. So it's a secular change of these conserved quantities, and this secular change of conserved quantities change in motion, and then the motion will be reflected in the waveform. So you basically can detect the waveform and to tell whether there is some axion cloud indeed around some massive black hole. So this is some plot for the ratio between this dynamic friction force versus the gravitational force or gravitational wave radiation force. You don't need this same ratio to be 1 to detect this effect. You just need this ratio to be roughly larger than 10 to the minus 5, because as I said, MRIs is a very sensitive probe for small forces. You just need this force to be larger than the gravitational force than 10 to the minus 5, and you can already detect the axiom, the dynamic friction due to axioms. Okay, so for these conservative forces, usually they don't contribute to the equation motion so much because they are kind of oscillatory, they average to 0. But then, so that means if they have comparable magnitude as the dissipative forces, the effect is usually much smaller. But across those resonances, where the orbital frequencies are commensurate with each other, one can show that these actual conservative forces can also change the conserved quantities like the Carter constant or angular momentum. So this is shown in this plot. Well, if we consider there is some third body around this MRI system, let's say third body is 100 gravitational radii away. So the gravitational field generated by the third body would also change. This is like a conservative force would change the MRI Carter constant and angular momentum across the resonances. Similarly, as people were saying that using MRI to test curl or test gravity what you are really trying to say is you want to test the modification of current metric. Okay, the modification of the current metric is a conservative change of the curve, and if you want to test that, you have to use these resonances. You have to try to probe the change of conserved quantities due to these conservative forces. Okay. Anyway, so these are very active research area right now, and people are trying to understand the emery dynamics under these small additional forces. Okay, so in the next few minutes, I'll briefly discuss the massive black hole binaries, which was mentioned before, right? They're the consequence of galaxy mergers, and after the galaxy merger, you form these binaries, and then in principle, the binary orbit shrinks because of, let's say, there's gas friction, or there is some scattering with the stars, but the detailed model is not well understood yet. So these sources are good multi-messenger sources because you expect to see X-ray, optical radios along the whole evolution path, right? So there's huge opportunities there. For example, if you look at the radio emission, let's say if you look at a simple system with assuming 2-point emission, radio emission sources, and for radio observers, you usually consider this so-called visibility, which is the Fourier transform of these radio intensity patterns, and this is observable. It turns out that if you measure this visibility, and then you can use that to reconstruct the orbit of this binary, like different, like the inclination of the binary, or eccentricity, or the semi-major axis to fairly good accuracies. And if you have additional measurement, let's say PDA measurement of gravitational wave due to these binaries, you can further constrain the binary mass to good accuracies. But for this particular radio observation, the separation cannot be too small. So for LISA, the separation will be, let's say, tens of gravitational radii. That's already too small to resolve by VLBI. That's why for this multi-messenger detection, we have to use PTA. But if you do have, let's say, tens of observations using LISA for this merger event of massive black hole binaries, you can still do interesting stuff with it. For example, if let's say you observe 50 merger events, so you can construct the merger density distribution using these events. And then on the other hand, from your optical surveys, the galaxy merger density, you can also get that, right? So comparing these two distributions, you usually would see a delay between these two distributions in redshift, because there's a delay between the galaxy merger and the binary merger. So one can use the gravitational wave events, right, to measure this delay time distribution. And once you, for example, this is some reconstructed delay time distribution, and once you measure this delay time distribution, you can use it to test predictions of different evolution models for the binary, let's say gas-driven model or a scattering-driven model, and etc. Yeah, so I'm just done. This is my conclusion slides. Yeah, so basically the emeries are sensitive probes for small forces. So their idea for studying fundamental physics and astrophysical environmental effects. And these massive black hole binaries are good multi-messenger sources, and they will help us to understand evolution paths after the galaxy mergers. Yeah.
Excellent. Thank you very much, Juan. I think there is a question already someone wants to ask. Eric, do you want to go ahead and ask?
Sure. Thanks very much for the talk. I was just curious, could you explain in a bit more detail the graph of the wet formation case, the one that had the gamma Emery label on it? I'm sorry if I missed some details there. I was just I wasn't fully clear on what was going on.
This?
Yeah, two slides below.
Oh, okay.
Yes, this graph right here.
Yeah. So
what is the gamma Emery?
Oh, this is the rate. So assuming this this black hole has a accretion disk, this is the rate per giga year for this system to have Emery.
Oh,
so
I
this,
see.
Yeah, so this rate depends on the mass of this central black hole, and this rate is usually much higher than those ones without the accretion disk, which is the dry formation channel. That rate is around 100. Yeah.
I see. Okay, thank you.
Okay, thank you very much. I think we are running over time, and there's been a question in the chat. And Juan, you feel free, please, to address the question if you wish. I want to thank at this point everybody, all the speakers of the today, and I hope I'll see you guys tomorrow. All our attendants. I want to ask the organizers as well if there are any closing remarks for today, or we should call it a day and then I'll see you everybody tomorrow. Scott or Jess or anybody else?
No, it was a fantastic session today. We look forward to seeing you again tomorrow. Thanks a lot.
Excellent. Okay, well, then I copy that. Thank you very much. It was a fantastic session. I learned a lot and it's definitely thought provocative. So see you tomorrow.